Hello everyone. So today we are going to talk about conjugate priors. So in our lecture today we are going to give a very brief recapitulation of what we mean by conjugate priors, and in this lecture we are going to discuss the conjugate priors for the normal distribution. Mainly, we are going to give the derivation of the posterior distribution for the assumed conjugate priors for the normal distribution. We will also look at the derivation of the posterior predictive distribution for the normal distribution, and we are going to also see how we can draw samples from the posterior predictive distribution or even the posterior distribution. We will look through an example how we actually draw samples from the posterior distribution or the posterior predictive distribution using R. First, we look at the definition of the conjugate priors. Let x be a random variable having the density f indexed by theta. Suppose script f be a class of density functions f indexed by theta, and theta belongs to the parametric space script theta, and x is a member of the sample space script x. A class P of prior distributions is said to be a conjugate family for the class of density functions f if the posterior distribution of theta given the observation x is in the class P for every x belonging to the sample space script x and for every prior distribution pi belonging to the class P. So, we look at an example. Suppose x is a random variable which is distributed as normal with mean mu and the variance sigma square. Here we assume that sigma square is known and mu is any real number. So, we all know that the density of the normal distribution with mean mu and the variance sigma square looks like that given below. Now, we assume that our class of prior distributions for mu, the parameter of interest, be a normal distribution with mean alpha and variance beta square, where alpha is any real number and beta is any positive real number. Here alpha and beta are the hyperparameters. So, the density of the prior distribution is as given below. Then it can be shown that the posterior distribution of mu given the observation x also follows a normal distribution, and the mean of the normal distribution is beta square x plus sigma square alpha by beta square plus sigma square, and the variance is 1 over 1 by sigma square plus 1 over beta square. Note that here the mean of the normal distribution is basically a weighted average, and the weights are actually the inverse of the corresponding variances. That is the variance of the random variable x and the variance of the prior distribution. So, we see that the posterior distribution of the parameter mu given the observation x is also normally distributed, and thus we may conclude that the class of prior distributions P is conjugate for the family script f, that is the normal mu sigma square family with mu taking any real number and sigma square positive is known. We further note that if we have, instead of a single observation from normal mu sigma square, if we have n IID observations from normal mu sigma square population, where mu is any real number and as before sigma square is a known positive real number, if we assume the same class of prior distributions for mu, then we can also see that the posterior distribution of mu given the data x, that is x1, x2, xn, is also normally distributed, and the mean of the normal distribution is beta square x bar plus sigma square by n alpha whole by beta square plus sigma square over n, and the variance is 1 over n by sigma square plus 1 over beta square. As before, we can easily see that the mean of the posterior distribution as before is also a weighted average of the mean of the prior distribution, that is alpha, and the sufficient statistic for the parameter mu, that is x bar, and the weights being the inverse of the corresponding variances, that is the inverse of the variance of the prior distribution and the inverse of the variance of the sufficient statistic x bar, that is sigma square by n. So, we next look at the derivation of the posterior distribution for the normal distribution when both mu and sigma square are unknown. So, we have x1, x2, xn IID observations from normal mu sigma square where both mu and sigma square are unknown. So, we consider the following prior distributions. The prior distribution of mu given sigma square as shown below, that is, it is normally distributed with mean delta and variance sigma square over S naught, these being the corresponding hyperparameters, and the prior distribution of sigma square is as given below, and this follows basically an inverse gamma distribution with parameters alpha and beta, that is, we have alpha and beta as the hyperparameters. So, this is conventionally known as the NIG prior or the normal inverse gamma prior for the above family of normal distributions when both mu and sigma square are unknown. So, the posterior distribution of mu and sigma square is basically proportional to the likelihood of the parameters mu and sigma square given the data x1, x2, xn and multiplied by the corresponding assumed prior distributions. So, the form of the posterior distribution is actually proportional to that shown below. Next, we are interested to find the posterior distribution of sigma square. From the above equation or the above proportionality, we can see that the coefficient of mu square is given by minus n plus S naught by 2 sigma square, and the coefficient of mu is given by n x bar plus S naught delta over sigma square. So, with these coefficients of mu square and mu in mind, the posterior distribution of mu and sigma square given the data looks like that below. We note from the exponent of the latter part that n plus S naught by 2 sigma square within brackets mu square minus 2 times n x bar plus S naught delta over n plus S naught mu can be written in the form as below, that is in the form of a square and some quantity, that is nx bar plus s naught delta whole square by 2 sigma square n plus s naught. So, with this previous consideration, that is splitting up of the terms corresponding to mu square and mu in the form of a square, we have that the posterior distribution of mu and sigma square given the data takes the following form. So, to obtain the posterior distribution of sigma square given the data, we basically integrate out mu from the posterior distribution of mu and sigma square given the data. So, we have that the posterior distribution of sigma square given the data is integral over the posterior distribution of mu and sigma square given the data over mu over the entire real line. So, taking into consideration the expression of the posterior distribution, the integral takes the following form. Note that the integral is actually the integral over the kernel of a normal distribution with mean nx bar plus s naught delta over n plus s naught and the variance sigma square over n plus s naught. So, the value of the above integral is basically the constant root 2 pi sigma over square root of n plus s naught. So, with a little bit of simplification, we can see that the posterior distribution of sigma square given the data actually leads to an inverse gamma distribution with the parameters n over 2 plus alpha and 1 over 2 summation xi square minus half delta square over s naught minus beta plus nx bar plus s naught delta whole square by 2 times n plus s naught. With the above posterior distribution of sigma square given the data and the posterior distribution of mu and sigma square given the data, we have from the very definition of the So, from the above posterior distribution of mu and sigma square given the data and posterior distribution, have the posterior distribution of mu given square and the data. So, with a little bit of calculation, it can be of mu given sigma square and the data is normally distributed with the mean nx bar plus s naught delta over n plus s naught and the variance sigma square over n plus s naught. Hence, we may conclude from the above that the class of prior distributions as assumed before, the class of prior distributions of mu given sigma square and sigma square are conjugate for the normal family of distribution. We can also obtain the posterior distribution of mu given the data by simply integrating out sigma square from the posterior distribution of mu and sigma square given the data. We can also obtain the posterior distribution of mu given the data by simply integrating out sigma square from the posterior distribution of mu and sigma square given the data. It can be easily seen that it basically leads to a t distribution with degrees of freedom 2 alpha plus 1 plus n, and we have also some scale parameter multiplied by it. Okay, so next we are going to look at the definition of the posterior predictive distribution. Suppose we have n IID observations from the density f indexed by the parameter theta. We have as the prior distribution of theta pi theta, and pi theta given x is the posterior distribution of theta given the data. Then the posterior predictive distribution of a new observation x star is given by the following. So, we look at an example, mainly the example of the normal distribution and the case where both mu and sigma square are unknown, and the assumed prior distributions as before. We also saw that the posterior distribution of mu and sigma square basically turns out to be the product of a normal distribution and an inverse gamma distribution with the corresponding parameters as shown. So, for just simplicity of notation, we let gamma equals the quantity n x bar plus s naught delta whole square over 2 into n plus s naught, and b square as the sigma square over n plus s naught. So, the posterior predictive distribution of a new observation x star from the very definition turns out to be of the following form. It can be easily seen that this also leads to a t distribution with degrees of freedom n plus 2 times alpha plus 1, and here also we have some scale parameter multiplied by it. So, how do we draw samples from the posterior predictive distribution? So, we have two methods. The first method is that we evaluate the exact analytical form of the distribution and we draw samples from that distribution, whether it is the posterior distribution or the posterior predictive distribution. There is also an alternative method of drawing samples from the posterior distribution or the posterior predictive distribution. In particular, here we are going to look at how to draw samples from the posterior predictive distribution from the previous example. So, the method is as follows. We draw sigma j square from the posterior distribution of sigma square given the data, that is, we draw an observation from an inverse gamma distribution with the parameters alpha plus n over 2 and beta star, where beta star is as mentioned before. Then, having drawn the observation sigma j square, we draw an observation mu j from the posterior distribution of mu given sigma square and the data, and we evaluate it at sigma square equal to sigma j square. That is, we draw mu j from a normal distribution with mean gamma and variance sigma j square over n plus s naught. So, with the observations drawn, that is sigma j square in the first step and mu j in the second step, we draw the observation xi star from a normal distribution with mean mu j and variance sigma j square. These observations xi stars are the samples from the required posterior predictive distribution. So, we look at next the definition of what we mean by highest posterior density credible set. So, the definition is as follows. Suppose x is a random variable with the density f indexed by theta, and we assume the prior distribution pi theta for theta. We have pi theta given x as the posterior distribution of theta given the data x. Then the 101 minus alpha % highest posterior density credible set for theta is that subset C of the parametric space script theta, where C is the set of theta belonging to script theta such that pi theta given x is greater than equal to some quantity k alpha, say, where k alpha is such that it satisfies the following condition. So, we turn back to the normal example and we have the usual assumptions for the prior distributions. We have also seen how the posterior distribution of the parameters given the data looks like. So, we also have the previous assumptions, that is, for the simplicity of notation we write beta star as the following quantity, gamma and b square. And we also saw that the posterior distribution of mu given the data is actually a t distribution with degrees of freedom 2 alpha plus n plus 1, and we also have some constant multiplied by it. So, lastly, we come to an example and we actually see how we can draw samples from a posterior predictive distribution. Suppose we have the data as given below. So, we enter the data in the R console, and first we need to check for the normality of the data. For that, we use the R command Shapiro.test followed by the observational vector x, and for the given data we have as our output of the Shapiro-Wilks test that p value is 0.4059. This supports that the data actually comes from a normal distribution. We also find the mean of the data and the number of observations for our given data. Let us assume some hyperparameters, and we have our regular assumptions of the conjugate family of prior distributions. We assume delta, S naught, alpha and beta are of the following values. So, from the derivation we saw that the parameters of the posterior distribution are as follows, and we compute them and we store them in the R objects gamma, b dot 2 and beta dot star. So, next we require to draw samples from the inverse gamma distribution. For this, we need an R package known as INV gamma, which can be installed and loaded into the R environment using the following commands. So, next we actually find the loop and we follow the method as mentioned before, and we draw samples from the posterior predictive distribution. We basically draw 10,000 observations from the posterior predictive distribution using the alternative method, and the empirical quantile of the observations we denoted by k dot alpha. So, this is what the k alpha value looks like. So, we saw that this is how we can draw samples from the posterior predictive distribution, and we can also find the empirical quantiles, and we can find the HPD credible set using R. So, to conclude, we saw today in our lecture the derivation of the posterior distribution for the normal distribution when both the parameters are unknown, and assuming conjugate priors for the unknown parameters. We also derived the posterior predictive distribution of the normal distribution we saw how we can draw samples from the posterior predictive distribution or even the posterior distribution by evaluating the exact analytical form of the posterior predictive distribution or by an alternative method. We also saw an example and we saw using R how we can actually draw the samples from the posterior predictive distribution or the posterior distribution through R. Thank you.